All right, welcome back to part 2 of Tuesday's lecture. So now we're going to be continuing with 6.8 and talk specifically about gravitational potential energy. So our first example of potential energy came from objects near Earth's surface, so near Earth. Should really specify surface because near Earth is very subjective. Delta U is approximately delta mgy, although y is really the only thing that's going to be changing there, more than likely. Now let's look at the general case for gravity. So the general case for gravity. So we know that comes from gravity, but generally, what does it mean to have gravitational potential energy? So, the force due to gravity, we know this well, is equal to minus g m1 m2 over r squared times the unit vector between them. So if we have a big star and a little star, this is a big star. And we've got a little tiny star. Now they're going to have a force between the two of them that is the same. So the force on the big star is the same in magnitude as the force that the little star is doing onto the big star. So we know this, we know reciprocity. Now, initially in this setup, both stars are at rest. And on axis. I mean, let's not work in 3 dimensions when we can work in 1. Okay, so since they start at rest and they're forcing on each other, we're going to see that they're going to start to be very attracted to each other. So they're going to start to move towards each other. So the force of gravity causes them to move closer, which is exactly what we should not be doing to each other right now. Not moving closer. All right, too soon? The small star moves further. So when we look at these two objects, it's pretty clear that because this large star has so much mass, it's going to move much more slowly, and it's going to track this one much more quickly. So the small star is going to move more than the large star, which makes sense if we think about it conceptually. But there's an interesting implication. So the small star moves more, moves more delta R, and therefore more work is done to it. Cool. So even, remember, I told you the force between the two of them were the same. Work is related to force times the change in displacement. This one is more displaced, so therefore it has more work done to it. Momentum principle and energy principle, 2 different beasts. All right, so note explicitly what I just said. The impulse and the change in momentum for the stars is the same. Work is different. So conservation of momentum still working just fine. All right, so we need to examine the potential energy. So we want to consider a system of both stars. So to examine, consider both stars. in one system. All right, so the work internal is equal to the force times distance 1 plus the force times distance 2. So let me just bring this back to play. So we're going to have, this is star 1, this is star 2, we're going to have distance 1, we're going to have distance 2. So we know this force is the same, so we can factor it out. This is equal to distance 1 plus distance 2 times the force. Delta U is equal to minus work internal. It's equal to minus F D1 plus D2. Now, since delta U is negative, the potential is decreasing, which means the kinetic energy is increasing. I think I'll actually write this down. So delta U is negative, implying decreased potential. Implies K increasing, which makes sense. We said they were at rest. Now they're moving towards each other. They've got a little bit of V, a little bit of non-zero V there. Okay, so just a little quick thing we could talk about. So we could look at a system with a small enough displacement that F is constant enough for the sake of the calculation. So then you would have delta U is equal to minus work internal is equal to minus F12 dotted with delta R1 plus F21 dotted with delta R2, and F12 is equal to minus 2F21, just reciprocity, rearing its head again. Therefore, you could say delta R2 minus delta R1 implies delta U is equal to minus F21 dotted with delta R2 minus delta R1. And this leads you to the result delta U is equal to minus F21 dotted with, oh goodness, I should show you the result, delta R. All right, so on your own, fill in these steps. So we're still going to have on your own components for notes. All right, so I want to introduce a concept that we're going to develop more and more and more in the classical class as we move through the course. So right now I'm just going to introduce it, and this is something that we're going to keep developing. So force is the negative gradient of potential energy. So du is equal to minus FR dr, and so the force is minus du dr. So this is the expression that potential energies of different forces are derived from. So for those of you that are in the classical class, for those of you in the general class, just know that these formulas that you're seeing are derived from here. For those of you in the classical class, we will eventually start working towards some of these derivations, and this is laying the groundwork. So should you choose to take what's known as a classical mechanics physics class, because you never know your future, you would see a lot of this. So it's not something that we would do too much of in Physics 3. All right, so Using this, we can get gravitational potential energy. So the expression for gravitational potential energy for any system is U is equal to minus G M1 M2 over R. So 211, optional. See where this comes from. It's a really cool little integral. Okay, but this is optional. All right, so R is the distance. And everybody needs to know this formula. Between two objects. And so what would happen if R was to get very large? So if we had, here's our chart, our graph of gravitational potential energy. Here's R, and so we see that looks something like this. So U is equal to minus G M over R. So as R gets very large, U drops to 0. All right, so here we have that. Let's go ahead and do an example. This example is based on a real-world interaction. So in February 2013, a large meteor with a mass of approximately 1.2 times 10 to the 7 kilograms fell near Chelyabinsk, Russia. I'm sure I just botched that. I could ask my stepfather. He speaks Russian. He could probably correct me. All right, so now I want you to know this exploded 30 kilometers in the air. So we only got some debris, still catastrophic, not as catastrophic as it could have been. But it's a fun little example to do because it's actually based in reality. All right, so let's consider this meteor. When this meteor fell from a distance of 1 times 10 to the 9 meters to 1 times 10 to the 7 meters. And we want to know what was the change in kinetic energy of the meteor. All right, so we're going to walk through this and we're going to really focus on the signs. Signs are tricksy and they can get you into trouble if you don't keep track of them. All right, so our system is going to be the Earth plus the meteor. Our surroundings, really nothing to do any work or force, so nothing that's interesting, you know. Jupiter's there, it's not making a difference. Okay, so the initial state is given in the problem. So we have a center to center distance of 1 times 10 to the 9 meters. So always make sure that you're dealing with center to center because that radius is the distance from here to here, not here to here. Okay. And then the final state, we have a center to center of 1 times 10 to the 7 meters. All right, we're going to calculate the gravitational potential energy for each state. And then we're going to use that to go after delta K. So it starts off with an initial potential energy of minus g m e m meteor over r I. So these are all numbers that we know because we know the mass of the Earth. So we've got our gravitational constant minus 6.7 times 10 to the minus 11. Well, the minus sign is, of course, coming from the equation. Newton meters squared over kilograms times the mass of the Earth, 6 times 10 to the 24 kilograms times the mass of the meteor, which we were given, 1.2 times 10 to the 7 kilograms, divided by the initial distance of 1 times 10 to the 9 meters. And so we see this is equal to minus 4.82 times 10 to the 12 joules. All right, I don't want to keep this along for the ride. So our final gravitational potential energy, so minus g me mass meteor over distance final, these two things haven't changed. So this is equal to minus 6.7 times 10 to the minus 11 Newton meters squared over kilograms times 6 times 10 to the 24 kilograms mass of the Earth, 1.2 times 10 to the 7 kilograms mass of the meteor, divided by 1 times 10 to the 7 meters. This is equal to minus 4.82 times 10 to the 14 joules. So we can see this is a smaller number. It's more negative than this, which is a bigger number. It's less negative. So UF minus UI is going to be less than 0. Okay. So using the energy principle, the change in kinetic energy of the meteor plus UF minus UI is equal to 0. Once again, we're assuming that the Earth is not going to have a change in kinetic energy, and we went ahead and just said we already know rest masses don't change, so 0. Okay, so delta K meteor plus minus 4.82 times 10 to the 14 minus 4.82 times 10 to the 12 is equal to 0. Therefore, delta K meteor is equal to plus 4.77 times 10 to the 14 joules. So this would have gotten you a negative answer, but when we bring it over to the other side, we have to add a positive to both sides, thus giving us a kinetic energy that is positive, which makes sense. We expect potential to decrease. We expect that it will get faster as it gets closer and closer to Earth's surface. So by paying attention to our signs, we got the result that makes the most conceptual sense. So this is why you can't actually trust yourself. Okay, so let's do another example. We have an exploratory probe from the Kuiper Mining Company. Lands on Dysnomia, which is a great name. And Dysnomia is one of Eris's moons. Eris is a dwarf planet that is beyond Pluto. How cool is that? And so the probe lands, collects a sample, and then blasts off to return to the main station on Triton, which is one of Neptune's moons. All right, so it turns off the blasters to conserve energy, or to conserve fuel. So naturally what happens as it gets further and further away is that it is actually going to slow down, because it's no longer going to have those blasters to help it overcome dysnomia's attraction. So let me give you some numbers for this. So the mass of the probe is equal to 2,100 kilograms. And when it is 350 kilometers away, so that would be 3.5 times 10 to the 5 meters, it has a speed of 16.2 meters per second. So this is when the rockets are turned off. And then when it is 750 kilometers, so that's 7.5 times 10 to the 5 meters, from center, so these are both from center, it has a speed of 6.8 meters per second. So here's dysnomia. Here's our probe. Here's the distance. So this is the situation we're analyzing, and we want to use this to calculate the mass of dysnomia. And I will tell you, these numbers are approximate. It's within the margin of error of dysnomia's mass, but there's a pretty big margin of error on dysnomia's mass at the moment. Okay, so this is the situation that we're dealing with. Let's go ahead and set up our system and surroundings. So we want to have some gravitational potential between the two of them. That's going to be the best way to do this. So our system is going to be dysnomia plus the probe. And in the surroundings, nothing. All right, so we're going to use M. That's going to be the mass of dysnomia, just to keep things easier. And little m is going to be the mass of the probe. You can always use your own notation as long as you tell me what it is. Please try to use notation that makes sense. So initial state, rockets off, speed of 16.2 meters per second. Final state, oh, and it's 350. The final state is going to be a speed of 6.8 meters per second and 750 kilometers from dysnomia. So the energy final is equal to the energy initial plus any work done. So we want an energy principle that makes sense. This is the one that makes the most sense for this particular setup. So let's flesh it out and find some cancellations. So we have mc squared plus kinetic energy of dysnomia final plus mc squared for the probe plus kinetic energy of the probe final plus the potential energy between the two objects final is equal to mc squared plus kinetic energy of dysnomia final plus little mc squared plus kinetic energy of our probe initial plus, oh, this is supposed to be an initial. Where was I? Plus initial potential plus work. All right, so where are my zeros at? So nothing's in the surroundings, so work is equal to 0. Let's see, these are on both sides of the equation. Goodbye. Also true here, goodbye. The kinetic energy of dysnomia, we can safely say, is not really changing, so those terms go away. And so we can rewrite that the kinetic energy of the probe final plus the potential energy final is equal to the kinetic energy of the probe initial plus the potential energy of the probe initial. So those are all the terms that we've got left. And we've got some expressions for that. So the kinetic energy is going to be equal to 1/2 the mass of the probe and v final squared. The potential between them is minus g m over the distance final, which is equal to 1/2 little m v initial squared plus minus g m over the initial distance between them. All right, so all of these terms have the mass of the probe in it, so it just kind of cancels out. I like it. I like it. All right, so building with this equation, we have 1/2 v final squared plus minus g m over r final is equal to 1/2 vi squared plus minus g m over r initial. So we can rearrange, get our r's on one side, get our v's on the other. So gm times 1 over r initial minus 1 over r final is equal to 1/2 vi squared plus vf squared. If those steps are confusing on your own, I highly recommend doing that algebra. Okay, so what we're after is we were after this. We want the mass of dysnomia. So the mass of dysnomia is equal to 1/2 vi squared minus v final squared over g 1 over the initial distance minus 1 over the final distance. Now we have an expression for the mass of dysnomia, all in terms of things that we know. Hooray! So that's 1/2 times 16.2 squared minus 6.8 squared meters per second divided by 6.7 times 10 to the minus 11 Newton meters squared over kilograms squared times 1 over 3.5 times 10 to the 5 minus 1 over 7.5 times 10 to the 5 meters. And we get the mass of dysnomia for this setup is equal to 1.06 times 10 to the 18 kilograms. So this is probably a little bit on the light estimation, but if you were to find this under those circumstances, that would imply the mass of dysnomia. All right, so we will stop. Actually, nope, there's one more thing I want to say. So just a couple more notes on this particular problem. So because dysnomia and the probe were in the same system, work was equal to 0, which led to a lot of nifty cancellations. It would have been very difficult to solve this problem using the momentum principle. Not impossible, but it would have required the iterative method and a computer. I would not make you do that step by step by step. So it can be done with momentum principle, but as we can see, by using the energy principle and thinking about how to set it up in a way to get some really useful cancellations, we actually made our lives a lot easier. So we are most of the way through 6.8, so that means Wednesday's lecture will start at the end of 6.8 as we start chugging through the rest of Chapter 6. So thanks so much.